Pochodzalla, I think that we should start, and so I think that in the introduction, people was coming. So good afternoon, Professor Pochodzalla, and good afternoon. Good morning. Sorry, good morning, and good afternoon. Thank you for joining. And today it is our great pleasure to invite Professor Josef Pochodzalla to give a talk. The title of his talk is From Neutron Stars to Strange Nuclei, strongly interacting matter on scalars from kilometers to femtometers. And so firstly, please allow me to briefly introduce our speaker. So Josef Pochodzalla is a professor of experimental physics at Johannes Gutenberg University. I'm not sure if my pronunciation is correct.
That's good enough.
Oh, thank you. Great. So he received the PhD at Max Planck Institute of Nuclear Physics, which is very famous, in 1983, and joined Yale University since 2000. His main research interest lies in experimental nuclear physics, including nucleon structure with electromagnetic probes and strength baryons in nuclei hypernuclei. So he is very famous for the work at various experiments such as A1 at Miami and Hi-Fi at JSI, Panda at FAIR, and Experiment 07 at JPAC. He used to be the spokesperson of the EU network SPHERE, and the member of the PRC editorial board. Now, he served as the spokesperson of WA89 collaboration, the spokesperson of Theater Network within Strong 2020, and the group leader of Compress. He has published more than 300 articles, receiving over 10,000 citations. So the H index is 58. So yeah, Professor, please.
Yeah, thank you very much. Thank you very much.
Recording in progress.
For these kind words. Of course, it's unfortunate that one cannot have the seminar in person, but nevertheless, because these online seminars are always the second best choice for seminars, because this direct interaction is of course missing. Nevertheless, it maybe is a chance also for the future to have easier exchange of ideas and discussions in these seminars. So before I start with the seminar, let me first set the stage. I mean, you will know that, of course, but leaving the Big Bang aside, a supernova explosion, as it is shown here, I have to switch something here, okay, is one of the most spectacular events which we have in our universe. It may shine with a brightness of about 10 billion suns, and the total energy release, one has to keep that in mind, which is about 10 to the 44 joules, is roughly the energy which our sun relieves in 10 billion years. So it's a really unique event. The time scale of this process, and also that will be important in a second, is of the order of seconds. So it's a long time scale compared to strong interaction or also weak interactions. The remnant of such an event, we all know, is of course either a black hole or a neutron star. What type is left, this depends essentially on the size of the protostar who is forming that. Indeed, the neutron star and the black hole are siblings. They have the same history in the evolution, and the only difference is that the mass of the protostar and For larger mass, you will form a black hole because the mass of the remnant is rather large. For a smaller protostar, you will produce a neutron star. One of the most intriguing questions is, of course, if we look at a neutron star, what is really inside such a neutron star? And that is essentially the topic of this talk. So I will start with the motivation, why we should study these objects. This will take some time. So this is also for those people who are not so familiar with this field, why we do that. And I would like to convince you that indeed the study of hypernuclei is an important issue for physics and for all of us to understand what is going on inside. And at the end, I will then briefly present one project which we are doing here in Mainz as an example of many projects which are ongoing in this field worldwide at the moment. Let me first begin with some history. Pulsars are already known since many, many years. And I mean, these supernova explosion, which were analyzed by Bard and Zwicky 90 years ago, essentially, they actually coined the word supernova, and they also speculated already about the structure of these neutron stars, which maybe left after such an explosion. Of course, we all know that it took very long to really observe then neutron stars in the form of pulsars by Jocelyn Bell in 1976. This is one of her notes from her book when he was a student there. Unfortunately, she didn't get the Nobel Prize, or not only the Nobel Prize, but his supervisor got the Nobel Prize, like it was probably typical for that time in last century. Today, we know that we have about 3,000 or a little bit more than 3,000 pulsars, which are known, and the frequency, the rotation frequency, which is, of course, our main observable, the changing frequency, the changing light emitted by these pulsars. These rotational frequency lie between sub-hertz up to a kilohertz, and already this kilohertz rotation frequency tells you that these must be really unique and spectacular stars, not conventional stars, which have much larger rotational times usually. Now, what do we know about neutron stars nowadays? Well, they are not very common. In our galaxy, we have about 100 million neutron stars. So it's not very many compared to 300 billion stars in our galaxy. Nevertheless, these objects are really superstars. They have a huge gravity. If you compare them to this value, which is essentially the Schwarzschild radius divided by the radius of the object, so the bending of the light in black holes, of course, this ratio is 1, this curvature. In the case of neutron stars, it's very close to 1. This already tells you that neutron stars and black holes are really close to each other. Of course, in our sun or in our Earth, these numbers are much, much smaller. Gravity, the bending of light, is, of course, hardly visible or very difficult to observe it. Now, these stars, these neutron stars, are really superstars, and that is expressed in the properties of neutron stars. They have a high density. This is what makes them interesting. They have a typical density, what we expect at least, is about 3 times nuclear matter densities or even beyond in the core of these neutron stars. They have a huge magnetic fields. Also, that is certainly interesting, causes interesting physics. They have this fast rotation, kilohertz, 10 kilohertz even. And they have, of course, super strong gravity in matter, which makes them unique, that you can study gravity in matter. And of course, we know gravity very well on certain scales, but we do not really know what is going on with gravity if it comes to strong gravity in matter. That is certainly a field for the future which might be very interesting. The fate of a supernova is essentially governed by the mass of the remnant that I mentioned already. So the final evolution of a supernova explosion and the end point of the process, whether it's a neutron star or black hole. That is again essentially given by the equilibrium between the gravitational pressure and the generated pressure. This is described by the so-called TOF equation, Tolman-Oppenheimer-Volkoff equation, which associate the pressure and the mass of the remnant. Of course, the additional thing we need is how easy you can compress this matter inside a neutron star, so the so-called equation of state here expressed in terms of epsilon as a function of the pressure. Generally, this equation of state, this governs really the mass of a neutron star. So if we have a soft equation of state, if that means if nuclear matter is easy to compress to reach a high density, that means the maximum mass of such a neutron stars it gets lower because it's easier to reach a high density, where we then have the conversion to a black hole, and we will have also a small radii. And if we have a stiff equation of state, we have higher maximum masses of a neutron stars and also probably larger radii. That tells you already that these two observables, radii and masses, very strongly associated with the equation of state, and this will be the point of these Earth-based experiments. Now, this is illustrated here in principle, and this we will see from nuclear physics, Earth-based experiments. We can try to get information on the equation of state, whether it's soft or stiff, for example. And this then plugging into the TOF equation, we can make predictions for the lines where neutron stars can lie. That means it's these lines, these mass radius relations do not tell you that the neutron star is moving along that line, but that's the end point of a neutron star where it will sit after it has been formed. And that can be, of course, then checked with astronomical observation. In principle, you see one very precise astronomical observation of a neutron stars with mass and radius would pin down the equation of state, or would fix the equation of state very on a high degree level of already. So the good thing is, in the past, we have now really many astrophysical observations. We have the pulsar timing, which is of course known since many years, which will give information on the masses. We have surface photon luminosity, X-ray bursts, supernova neutrinos. All these tools came up in the last 10 years. And we have, of course, which is also very important, gravitational waves, because they tell us something also about the radius, because when two objects touch, the shape of the gravitational wave will change, and also they will tell us something, since the deformability will change the moment of inertia, this will also change the rotational curves. So we have many tools, and there are two main experimental devices we have. This is one on one hand, we have these gravitational wave detectors, LIGO, Virgo, and Kaga. Until now, they have roughly, I think the number is now increased a little bit. It's about 100 events they have observed of gravitational waves. That means of the merger of heavy objects, mostly, of course, black holes, but also neutron stars with neutron stars, or a neutron star with a black hole. And this is an important source of information, as we will see. And on the other hand, we have the nicer experiment on the ISS, which observes the rotation of neutron stars, in particular the rotation and the variation of hot spots on these neutron stars. So you see already neutron stars are not really homogeneous objects like you might imagine that. So different from a black hole, which is essentially structureless, which is only geometry. It may, of course, rotate. Neutron stars are interesting. And they are particularly interesting because this is the only object which combines all four fundamental interactions which we know, and where all four fundamental interactions, strong, gravity, weak, etc., they play a role in these neutron stars' evolution. Now, neutron stars, of course, this is the question. Nevertheless, they are very difficult to observe because they are tiny. We have seen their typically diameter is 10 kilometers or so, as will be shown in the next slide. Nevertheless, there have been masses established now for many neutron stars mostly from binary systems, because then it's easier using the Capellian laws to determine the mass of these neutron stars relatively precisely. You see the majority of neutron stars have a typical canonical mass of about 1.4 solar masses. But we have also neutron stars which are extremely heavy compared to our solar mass, namely up to about 2 or slightly above or below 2 solar masses. And some of these masses, around 2 solar masses, are very well known in the universe. Now, as I said, behind all that is the equation of state. And that is something we can address on Earth. And this equation of state, I think, is a holy grail for nuclear physics, since we do nuclear physics, nuclear reactions, at least half a century already. The only known point is, of course, that we have at temperature 0, when we plot here net baryon density and temperature, the only well-known point is, of course, the ground state of nuclei. Normal nuclear matter density and temperature 0. And everything else needs to be explored by nuclear reactions on Earth. And that we have done and do still and will do in the future, of course, in many places on Earth. One has to keep in mind, though, that these reactions which produce very high densities or try to produce very high densities are the matter which is produced in these reactions. I have seen the star experiment, also in the star experiment. This is quite different from what we have actually in neutron stars, because in these heavy ion reactions, you produce usually a lot of pions, and you have isospin symmetric matter. That means protons and neutrons. So protons, you asked a question?
No, I don't think this is a question. Yeah.
So neutron stars are really different from what we can probe on Earth. One always has to keep that in mind, that one needs, of course, some extrapolation, some additional tools to come to the matter which we have in compact stars. So this is one caveat. Now, from these based experiments, of course, we can try to extract the equation of state. Usually one can so to say, express this equation of state in some Taylor expression as a function of density and the and the difference between neutron and proton densities. One has this isoscalar part which reflects the density, and then we have this isovector part which is dependent on the isospin of the system. That, of course, is an approximation which will certainly break down at very high density. So this is a very naive and analytic approximation. Usually, in order then for the physicists to keep that very simple, this is then often reduced to 2 parameters. There are more parameters in that equation here, but essentially the main parameters is always the so-called symmetry energy, which we can deduce from many experiments on Earth and also from experiments in space, and the slope parameter L, so-called slope parameter L in this equation of states. So this is a very simplification of this equation of state, and of course this is very, one should always keep in mind that this is, that the equation of state of nuclear matter is much more rich than expressed in these 2 quantities. What is shown here in the plot is now a plot of these 2 main parameters, the symmetry energy S0 and the slope of the symmetry energy L, deduced from many observations from starting from, for example, neutron skins in nuclei, from neutron stars, that's the red band here, from other experiments on Earth. And you see they all lie somewhere here around 60 for the slope of the symmetry energy, for the slope of the symmetry energy, and about 30 or so for the symmetry energy. This is already good news, and this is a little bit better expressed here. What I show here is a plot von Bauer-Lee. This is the slope of the symmetry energy. Now, the experiments on Earth roughly give this range here between these 2 purple lines. So there are many analyses going into that, many observables from Earth-based experiments. So it of course has a large variation, but nevertheless it's around 60 plus minus whatever, 28 or 60, depending how you analyze these events. And the important thing is here, these other symbols which are shown here, these are different analyses of astrophysical observations, and they deduce the same quantity from gravitational waves, from NISA observation, etc. And what you see here, that both of these type of experiments give very similar values of this one quantity, the slope of the symmetry. That is an important message because it tells you that nuclear physics and hadronic physicists speak the same language like the astrophysics community. So we can really communicate each other and really bring these two fields together. That is very important, I think. Now, this is, of course, what can be has been done by NISA and also by the gravitational wave. They can determine the radius. NISA particularly can determine the radius of a neutron star and the mass simultaneously. Not for many of these neutron stars, roughly a handful of these, or few have been observed by NISA at present. But they can, of course, already pin down the equation of state. Particularly, one of the latest observation of a heavy neutron star around 2 solar masses and the radius. So you see all these only mass radius relations are allowed, which will pass these areas here. And you see, although this narrows down many equation of states, which are outside of this area, which are not shown here in this plot, but it still has many, many possible solutions, unfortunately. So we have to wait for better and hopefully more data from NISA coming in the future or from the follow-up experiments. Of course, many of these equations of states have different degree of theoretical robustness, so not all of these equations of states, which are shown in the plot here, are really equal. Indeed, there are also equations of states which contain hyperons, because hyperons, as I will show you in a minute, are allowed in these neutron stars. But you see in the beginning, and this we will have I will discuss briefly now, that most of these hyperonic equation of states predict only very low maximum neutron star masses. Now, why should there be hyperons in neutron stars? This is also an old story, which goes back to Cameron, 1959. And he already speculated that also hyperons and maybe even heavier mesons may be in the core of neutron stars. And the argument for that is indeed extremely simple. And this is, it's an energetic argument, so it's valid. I mean, if in the neutron stars you have baryon densities of about 2 to 3 times rho zero, that means the Fermi level of the neutrons will be moving up in the Fermi potential. The time scale of the explosion, I mentioned that, is of the order of second of a neutron star, so the formation of this neutron stars, the time scale is of the order of seconds, and that is much larger than weak interaction. That means hyperons can be formed by converting neutrons into hyperons, because if the Fermi level is higher than the mass of the lambda hyperons, it's energetically favorable to convert a neutron into a hyperon, particularly in a lambda or in other hyperons, of course, in principle. So once they appear, these hyperons, they are stable because the decay is Pauli forbidden, because levels are occupied by neutrons in these neutron stars, the other levels, so it cannot decay. So this is a very simple argument. And if you calculate that, you find that this should happen at a density without interaction at a density of T of about 5 times rho zero. Now we have, of course, interaction, our equation of state. Hyperons, nucleons interact among each other. So this will change the simple picture. And with interaction, we know from the simple argument that hyperons should appear at a density of between about 2 or 3 times rho zero. So this is very general. Now the problem comes when these hyperons appear. You have a new species inside the neutron stars. That means you will relieve the Fermi pressure, because besides neutrons, you have then also lambdas or cascade hyperons. And that will, of course, soften the equation of state. That means as soon as hyperons appear, the equation of state will be softer. You can compress because you have two different species, hyperons and no conventional nuclei. This will reduce the maximal mass of a neutron star. And this appearance of the hyperons, that was the first, when then suddenly the first, not suddenly, but about 10 years ago, the first very precise observation of a neutron stars with two solar masses was done by Demarest. It causes a problem because when hyperons appear, they should weaken the nuclear equation of state, and that should then reduce the maximum mass of neutron stars. And that is called the so-called hyperon puzzle. Of course, nowadays, and this was very intriguing, this problem, so we now know that this appearance of hyperon depends not only on simple nucleon or two baryon interaction, but also free body interaction play an important role. And there are indeed equation of states which include hyperons, which include no hyperons, or which include even more exotic matter inside the core, which can describe these very heavy neutron stars. So unfortunately, or fortunately for the scientists, because we have something to do, these present terrestrial data and also the astrophysical observation do not yet allow to uniquely determine the equation of state. That tells you that more data and more precise data are needed. Now, in order to study free body interactions where hyperons play a role, because I tried to convince you that hyperons should be there, of course, the main tool will be hypernuclei. Scattering experiments of hyperons or correlation studies of hyperons in STAR or ALICE or wherever are, of course, important for the two-body interaction. But if you in detail free body interaction, you have to go to nuclei. And hypernuclei and also conventional nuclei, we don't know that, are affected. The binding of these nuclei are affected by free body forces. That means hypernuclei, good tools to study free body interactions. So it's a very unique way to do this study. You see here the effect for a specific free body interaction are important. In turn, you can turn this around. Studying of hypernuclei will be important to really determine free body interactions, not only among nucleons, but also hyperons and nucleons, or hyperons and nucleons. So this is the motivation why we want to study hypernuclei. And in principle, now a very brief introduction to hypernuclei, to those who are not so familiar. In principle, there are two ways to study hypernuclei. Hypernuclei are nuclei where we embed one hyperon inside the nucleus. And usually these hypernuclei will decay with a time scale, with a typical weekly time scale of 10 to the minus 10 seconds. So they can be observed by the decay, of course. When, of course, doing a decay spectroscopy, there are many tools you can study, like in conventional nuclei, gamma ray transition in these hypernuclei. You can study the pions from the weak decay. You can measure branching ratios. So there are many things you can measure. Usually that is restricted to light nuclei, because once it comes to heavy nuclei, studying the decay gets very difficult, because you produce quite a number of neutral particle or gamma rays, and then adding up all these particles is very difficult. So decay studies are usually limited to light nuclei experimentally, and also lambda, so double lambda nuclei decay studies are usually important, because otherwise it is very difficult to study lambda hypernuclei with the alternative process, namely the direct production in so-called missing mass experiments, here shown on the left-hand side. That means you have an interaction of a projectile B on a target, you produce some strangeness, for example, in a chaos, and you implant a lambda particle inside the nucleus, and you measure by missing mass the produced lambda hypernuclei. By measuring precisely the outgoing fragments, 1 or 2, depending on the type of process. In this case, which is important, the direct detection of the hypernucleus is not required. That makes it ideal to study not only ground state, but for example, excited states which decay. Unstable states can be studied by missing mass experiments in principle. Of course, experimentally, it's a little bit more complicated because usually you need secondary beams, mostly pion beams or kaon beams. There you convert a kaon into a pion or a pion into a kaon to bring in the strangeness into this nucleus in the target region. There are also electroproduction possible. In this case, if you have an E prime K reaction, like it has been done at JLab or is being done at JLab, for example, you need to detect, of course, both particles, the scattered electron and the kaon. So this makes things a little bit more complicated. And of course, you can, in principle, do also things you can produce very heavy nuclei depending on the target you use here. Yeah, because you can study not only the slight nuclei like in the decay studies, but very heavy nuclei in principle. And probably this is also these missing mass experiments are really unique to study very heavy nuclei beyond, let's say, mass 20 or so. Examples in the case here I mentioned already, it's essentially pion beam and electron beams. In examples for these decay studies is, of course, nuclear emulsion, heavy ion reactions like in STAR or in ALICE, or at other experiments, antiproton-induced reactions, etc. So indeed, this field is very active since, of course, hypernuclei have been studied since now about 60, 70 years. It started all with nuclear emulsions, essentially. So this was already indicated as these events are rather rare, and these events are still today rather rare, so it's very difficult to study hypernuclei. But you see the landscape of laboratories where hypernuclei are of interest is really increasing, and you see it's, of course, in China, HIAF will hopefully also study hypernuclei in future. JPARC is certainly an important experiment and will be an important experiment in the Hadron Hole to do this nuclear physics. And then STAR-RIC and also ALICE, these heavy ion experiments are very important in our field. And then there are many experiments, many laboratories who do dedicated measurements, like at MAMI, I will show you in a second one example, or at ELF, where specific nuclei are studied in more detail. What is interesting is simply the number of publications that was rising. So this was in the 60s, 70s, this was the so-called emulsion area here. I will try maybe here with the laser pointer whether this works. The emulsion area for many years, of course, there only very few events were found and could be analyzed. Then we had the first accelerator experiments at Brookhaven or CERN with kaon beams mainly. And nowadays we have a steady publication rate, I would say, of roughly 1 publication per week. So 50, 60, 70 publications per year, and a lot of citations, of course. So this is now a well-established physics at many, many laboratories, big laboratories, of course, like FAIR, hopefully in the future, Jefferson Lab, JPARC, and also in China, hopefully in the future, and also in LICA. And then do you have these dedicated experiments like at Daphne here, for example, or at other places here at ALF. So this is the long introduction to that field, and hopefully you have understood why this field is so interesting, not only for me and hopefully also for that. Now I will come to one specific example, and this is the example of the hypertriton. The hypertriton, mass-free, is indeed the simplest nucleus, simplest hypernucleus, It is, of course, an ideal object to study free body interaction. It's like the deuterium for conventional nuclear physics to study the nuclear-nucleon interaction. The mass-free hypernuclei are also important cornerstones. What we know is that only, presently at least, the only known bound hypernuclei is the so-called hypertriton, consisting of a proton, a neutron, and a lambda particle. We know the branching ratio of the decay of this hypernucleus, which is about 0.3, and we know that the binding energy, as I will show you in a second, is very small. The ground state spin is 1/2, so we do not have evidence at the moment for a bound excited state of the hypertriton, which in principle could exist, but it doesn't seem to be there at the moment. This is our knowledge. Whether there's an unstable state, this is still an open issue. And maybe this can be answered by folks in Starr or Ellis when one studies correlations between a lambda particle or deuteron or free body correlations. We have no conclusive evidence yet for a neutral NN lambda system. There were some indications by the Haifa collaboration at GSI. This is presently studied again at the GSI. It was studied with the VASA experiment there, and it was also studied at JPARC. At JPARC, there were no evidence found for this neutral nucleus, so this is something we still have to wait. The question in the following part of the talk is the question, do we understand the simplest hypernucleus? And how well do we understand the simplest hypernucleus? And we will see indeed that our understanding is still limited. Not everything is known to a certain level of precision as we wanted to have that. Now this shows you the first part of the so-called hypertriton puzzle. The first part is the binding energy. This is, of course, something you would like to know from each nucleus, from any nucleus you study, and the binding energy has been studied in emulsions very early already. In this time, the typical binding energy were of the order of 130 keV or so. Of course, the problem with emulsion is that it's not very well documented what is the systematic error of these measurements, because this is very tricky to determine really very precise. In the past, then, heavy ion reactions, Alice and Starr also produced the hypertriton. This is, so to say, also the domain of these heavy ion reactions, where these hypernuclei are produced by some kind of coalescence mechanism. So that's also these light nuclei are in particular those which is really unique for these heavy ion experiments. You see that the Alice data and the Starr data are a little bit in conflict, although the error bars, of course, one should admit that is rather large. So presently, if one takes all these measurements together, the measured value of the binding energy is very small. It's about 150 keV. And that, of course, has implication. What does it mean for the structure of this nucleus? Well, the structure, it means it's a very dilute system. If you consider a near threshold S state, and that is just solving the equation of state, you find that the scattering length is of the order of h bar over 2 times the square root of the 2 times the reduced mass and the binding energy. And if you simply use this equation to calculate that for the hypertriton, this 130 keV binding energy, you find that the radius of this nucleus, that means the radius of the lambda particle in this hypertriton, is of the order of 10 Fermi. So it's a huge nucleus, much larger than a lead nucleus. It has a large tail of the hyperon, and that, of course, has implications. The first implication, and this is now something the Starr people here in the audience know very well, is the question, how could you form such a system which is so dilute in these very extreme and hot interactions at Alice or at star. I think this is something which is very interesting and very intriguing. Braun-Munzinger named that the snowball in hell. And indeed, this is something which, of course, one qualitatively maybe can understand, and one can produce models who do that. But it's certainly intriguing how in the hell such a dilute system can be produced in very dense nuclear systems. The other part of the puzzle is the lifetime, because if you have such a dilute system where the lambda particle is far away from the core of the formed by the deuterium, you would naively expect that this lambda particle is essentially a free particle, a free lambda. And that means it should decay with the lifetime, which is the same like the free lambda. And it was puzzling until about 2016 or 18, because at that time, after first measurements in bubble chambers with large error bars, they came up the first heavy ion results. And the tricky thing is, or the funny thing is, that all these three studies very close in time here produced lifetimes which were significantly lower than the lifetime of the free lambda particle. And that was then phrased the so-called Hyperon puzzle, because on one hand, a very small binding energy, on the other hand, a very small lifetime compared to the free lambda lifetime, that didn't fit together. In the meantime, we have from these heavy ion reactions from Alice, also star, new data, new measurements which come closer to the free lambda lifetime. If we calculate that and take all these values together, we find a lifetime which is 140, 137 picoseconds, so a little bit lower than the free lambda lifetime here indicated by the dashed line. So in the meantime, is there still a hypertriton puzzle? I would say no, because we have now a lifetime which is closer to the free lambda lifetime. We have some information on the binding energy, and I think what we have now is a more quantitative problem. It's now a question of precision. How well do we understand the system? Here in this plot, what I show here is the binding energy and lifetime. That's a probability distribution with the presently measured lifetime and the presently measured binding energy. This is this purple area. So here the centroid lies around here. And these are, for example, theoretical calculations, which of course still do many approximations, but they come very close already into this region. They predict lifetimes which are a little bit shorter than the free lambda lifetimes. So in the presently, first of all, what is important is, of course, that we come closer. That means it's now the question for nuclear physicists to really determine that with a very high precision. The main reason why this lifetime is here smaller than the free lambda lifetime seems to be the pi and final state interaction, which is important in the decay of these hyperons. So this is now a quantitative question, and so we are now approaching or going away from this word hypertriton puzzle, but we are approaching now an area of precision and accuracy. And for that, we need new experiments. There are a series of new experiments coming up. I will tell you and show you in the remaining part of this talk the experiment at MAMI we are planning or have done already. There we are aiming at a binding energy precision, which is in the range of 10 plus minus 30 keV systematic error. Then there are many other experiments coming up. One will be at JLab, where they will also look for the excited states, whether this exists. There is a measurement at ALF for the lifetime. At JPark, experiments are planned. And of course, also these heavy ion reactions, once they can produce more and more data, they will also, of course, provide more precise measurements of both the lifetime and, of course, maybe also the binding energy. This shows you here the quest for the precision. Why do we need this precision in order to pin down also the interaction? This is a calculation from the Prague group, here shown here from Daniel Gasta mainly. And this shows you really the effect of many different NLO interactions, and you see the variation, the typical variation by this interaction is very small. That means we have to determine the ground state binding energy or the ground state energy very precisely. This is not the binding energy, this is here the ground state energy here, plotted here. You see, we need roughly a precision which is in order to pin down these interactions of the order of few keV. Before I come to the Mainz experiment, I would like to mention at least one experiment which is planned at NuStar, at FAIR or GSI in the near future. This is namely an experiment to measure directly the interaction cross-section of the hypertriton. The idea is very simple. If this hypertriton is as large as we expect from this simple consideration I have shown, it should have a large interaction cross-section. And the way to do that is these hypertritons will be produced in heavy ion reactions, in forward direction, in projectile fragmentation. This is shown here. And then you have a secondary target inside an active detector where you detect the decay. And depending on the thickness of the primary and the secondary target, and on the cross-section in the secondary target, you will observe different yields as a function of the decay vertex. So this is very unique, this experiment, and this will hopefully give us an answer whether the simple picture which we have of this extended object is really true or not. I mentioned already future experiments of the mass measurement. This is what we are doing at Mainz. We do not measure the lifetime work, but we measure the mass, and I will go into that. And here you see other experiments and analysis. Here the EO7 plans to analyze emulsion data, and they hope to receive accuracy of about 30 keV. One has to see, of course, whether the systematic errors in these emulsion data really is as small as we hope for. And then, of course, Alice and Star, I don't have to talk that. Now let me come to the Mainz experiment. The Mainz experiment, we use the pion, so-called pion decay spectroscopy. That means a two-body decay of a hypernucleus. If a hypernucleus decays at rest into a remnant and into a pion, so a two-body decay, it's completely sufficient to measure the momentum of the pion to determine the mass of this hypernucleus. Because the remnant is, of course, known, because these pionic momenta are unique fingerprints of a specific nucleus. And the pion mass is known, the mass of the remnant is known. One momentum is sufficient to determine the mass. And this is done in Mainz in the following way. We shoot the electron beam on the target. In the first experiment, we used the beryllium target, which we have done a couple of years ago. And we measured the pions in two big spectrometers with very high resolution, with 10 to the minus 4 resolution. That means with very high precision. In addition, of course, since these reactions producing hypernuclei not very often, we need a spectrometer to which signals us that their strangeness was produced. So we have this so-called chaos spectrometer from the GSI, where we detect the kaons for suppressing the background. What did we observe in this experiment? This was the pion momentum spectrum, which we observed a couple of years ago. And this signaled the decay of the hydrogen 4 lambda into the pion and the helium 4. One knew from emulsion that somehow this pion momentum should be in the range of about 130 MeV/C. So that's why I say each nucleus, each hypernucleus has a unique fingerprint, a unique value of this pion momentum. And we could measure this momentum with very high statistical precision, 20 keV. The uncertainty we had in this experiment, and this was then the main issue for now doing the new experiment for hypertriton and what we had to improve, you see we still had a large systematic uncertainty. And that systematic uncertainty is mainly due to the absolute calibration of the spectrometers, which we do by our mummy beam. You scatter elastically electrons on a target, and these elastically scattered electrons are used to calibrate the spectrometers. Of course, if you have an uncertainty in the absolute mummy energy, you have also then, this translates into an uncertainty of the calibration of the spectrometers. In order to improve that, we have obviously to determine the absolute mummy energy. Usually for many experiments, like at STAR, etc., where you are, the absolute energy of a heavy ion beam or other beams is not so important. In our case, it's important because it enters into the calibration. We do so by a new method, which we have developed over the last years, by the interference of radiation from two undulators. The other thing which we have learned from this experiment, from the first experiment, is that we need more luminosity, because any reasonable calculations predict that indeed the hydrogen 4 lambda is the most common nucleus produced in our reactions, which we do at MAMI, and that the hypertriton, the production cross-section of the hypertriton, is roughly a factor of 10 or 8 lower compared to the hydrogen 4. And that was the reason why we could not really have a statistically significant observation of the hypertriton in this first experiment. That means, besides the absolute calibration, we also have to improve the luminosity in the forthcoming experiment. And that we have done by now using a very thick target. What we use or have used in the last year for the experiment, we have used a lithium target, and we shoot the electron beam along the 5 centimeter long lithium target, inside this lithium target. The spectrometers or the pions are emitted to the side, so they transverse only a little bit of material. Lithium is not very dense, so 1.5 millimeter lithium, or in the experiment actually we used 1 millimeter, a little bit than 1 millimeter lithium. The energy loss variation is rather small, so the statistical accuracy remains, but we have a much thicker target now available. That means we have much thicker luminosities. And this works. You see here, for example, by a thermal camera, the picture of the beam inside the lithium target, which is of course heated up. And if the alignment is not perfect, if the beam does not really hit the 1 millimeter lithium target here, you see that this by half only the target is illuminated by the beam. The other thing is that we use undulator radiation for the absolute calibration of the MAMI beam energy. How does this work? You use 2 undulators as a source for X-rays, and you can move one of these undulators, and by moving one of these undulators by typically a meter or so, you can observe the interference of these 2 wave packets. That means it's essentially a 2-slit experiment we perform. And for specific wavelengths, which you can then select by a monochromator, you will find intensity variation, which is indicated here. This is what you expect. And this wavelength typically of this intensity variation by changing the distance of these 2 undulators, this wavelength is of the order of 10 centimeters. And this wavelength is directly related to the gamma of the electron beam. That means to the energy of the electron beam. You have to measure, this sounds now very trivial, it isn't really trivial because it's very complicated and you remove all systematic error bars, but in principle you do 2 measurements of 2 length scales, of this oscillation length here and of the wavelengths of your radiation, which you can select very precisely with the monochromator. So this lambda rad, this can be determined very precisely. What you measure is this oscillation length. And that is nice because you don't need a magnetic spectrometer or some other devices to measure the MAMI beam energy. You just do 2 length measurements. The measuring lengths in principle of the order of 10 centimeters should be very simple. Now what is shown here is now the plot of MAMI, how MAMI really works. this was an experiment we have done before with a magnetic spectrometer, where we also have tried to measure the absolute beam energy. What we could, the blue points here are, for example, MAMI beam energy measured by the operator at the MAMI accelerator. And you see there are some fluctuations. This is actually the uncertainty, which I have mentioned before, the 160, 180 keV. And here is actually the measurement by this magnetic spectrometer. What this shows is that the MAMI beam is much more stable than the measurement of the MAMI accelerator crew tells us. It is stable. Of course, this was a measurement where we could not measure the absolute energy, but the variation of the MAMI beam. And this is now here a picture of the undulator set up. These are these two undulators. The blue undulator is moved along the beam line. Here you see the beam line of the electron beam. And here you see the observed oscillation for one specific wavelength. And now you have to analyze that, and that has been done by Pascal Clark in his thesis. Here you see, for example, 3 measurements of the MAMI beam energy at different times. And at that time, MAMI was not, since we had to change always something at MAMI, the absolute energy could change slightly because the setup was changed and MAMI was not running stable in the short time. And here you see the old measurements by MAMI, and the green points here are now the beam energies measured by this undulator map. As I said, in the true calibration of the spectrometers, we will run MAMI and also the undulator setup for longer time, so there will be no temperature effects, etc., which is the reason for this variation here of the MAMI energy. So we have both kinds of both inputs which are needed to do a new experiment. We have a higher luminosity with the lithium target. We have a better, hopefully better, absolute calibration of the spectrometers. And this was the point then where we performed the experiments in later last year, in October last year. The analysis is still ongoing. Here is a raw diagram of a couple of runs where we can already see the pi-pi coincidences. One pion in the kaon spectrometer and one pion in the other spectrometers, in high-resolution spectrometers. The kaons, the k-pi coincidences, which are, of course, interesting for us, they are still hidden here. So this still needs to be cleaned up, and all the cuts, etc., needs to be applied to. So the analysis just has started mainly from our Japanese colleagues, and hopefully in a couple of months, we will have first results of this experiment. So what is the take-home message now for you? First of all, strangeness nuclear physics is embedded in the quest really to determine the equation of state, in particular also the equation of state, which is then relevant for dense stellar systems. Hypernuclei indeed are important laboratories, and also hyperatoms, like we talk about that, to study these hyperon nucleon interaction, not only two-body but also multi-body interactions. We have still many puzzles. So the hypertriton puzzle, this is now really a quantitative problem, I think, in the future. But for example, the existence of the neutral hypernucleus or other neutral hypernuclei, the Hyperon puzzle of the neutron star, this is still something which is, I think, to be honest, a long-term goal, which will not be answered by a simple experiment. We have many studies now. This is good because we have competition, but we have also obviously interest in this type of physics. And we will have, hopefully in the next couple of years, new generation of experiments which focus more on precise studies, not so much on discovery experiments. And of course, one should always say that these studies need to be, and this is the good thing, they are indeed embedded in the theoretical evolution, effective field theories, lattice, etc. All this is coming up and really will contribute to our field. And last but not least, I could cover not many things I couldn't cover, which we are doing also in follow-up at Mainz. I should say here, for example, missing mass study of the hydrogen-6, which is a very neutron-rich system where one of the students from Fudan, Tianhao Shao, is involved in his doctoral thesis. But we have also other projects which I could not cover, which shows you really how many beautiful experiments you can do in the field of heavy ion physics. Yeah, Thank you very much for your attention.
Thank you very much for a very comprehensive talk on the dense matter from neutron star to hypernuclei. I think we have a couple of minutes to take question. So let's see any question. Yes, yeah, please, 张博元是吧？
Okay, can you hear me?
Yes.
Oh, yeah. Yes.
Okay, first I have a very naive question. What is the most simple hypernuclei? It's hydrotriton instead of hydrodeutron.
Well, there are no two-body systems which are bound. So lambda and the neutron or proton are not bound, that we know, and all the other hyperons, so cascade and the nucleon, they are not bound. So there are no bound systems.
There are no bound system for hyperdeutron.
Which are lighter than A equal 3. So the A equals 3 is the lightest nucleus.
Okay. And another question is about the two-body decay measurement. So how could a lithium target increase the luminosity?
The luminosity is increased because in the target needs to be very thin, usually, because yes. Because the hypernucleus is produced inside the target and is stopped, because we are looking for the decay of a stopped hypernucleus. Now, if this target is too thick, you will have, of course, energy loss straggling in the target. That means you have a large wide peak. This peak, which you see here, will be widened by the different energy losses in the target. That means in the first experiment, we used a beryllium target, which was bent a little bit in order to minimize the material seen by the pions when they move to the spectrometers, but we could not use the thick target. In the case of lithium, and that's what there are two reasons why we went to lithium, is first of all, we expect that in the case of lithium, we have no other hypernuclei which are produced, which could produce some background. There's specifically one hypernucleus which could produce a pion momentum very close to the pion momentum of the hypertriton. This is one reason. The other thing, in the case of lithium, you can use a very thick target, which is indicated here. You shoot, since the mummy beam is very precise, it's a tiny beam of a few hundred micrometer thickness. We can shoot the beam into the lithium target alongside. So we have a thick target. On the other hand, the pions are detected at 90 degrees relative to this target. So they transverse only a little bit of material. And lithium has also the advantage that it's not a very dense material. So the energy loss variation in this, typically a millimeter of this target, is very small. So we still have a sharp peak of the pions, but we have a thick target for the electron beam. So a 5 centimeter instead of a few hundred micrometer target. And that gives us in total a factor in the luminosity of about 50 or so.
Okay. So what's the original targets you've used before?
Before we had a beryllium target. It was a beryllium target which was bent slightly. I don't know whether I can use a pen.
Beryllium.
Yeah, it was beryllium 9. So you produce these hypernuclei in a fragmentation reaction. You shoot on a target the electron beam. You produce, of course, an excited system, and eventually it will produce a kaon. And we use the chaos spectrometer to tag this kaon here. And this pre-fragment then, which may contain a lambda particle or not, is excited and will eventually decay into the hypernucleus we want to study. And this hypernucleus, the energy of these hypernuclei in these decays is usually very small. They are stopped to a large percentage inside the target and then perform the two-body decay. So it's a multi-step process to produce these hyperfragments, these hypernuclei, or the hypertriton or hydrogen 4, which then decay and emit the pion into the spectrometers.
Okay. Thank you.
So it's not. It's like the reaction which I have shown here. It's like these emulsion reactions, if you like. These kinds of it. It's a decay spectroscopy. We do not missing mass spectroscopy. We only use this chaos spectrometer to see the chaos in order to reduce background.
Okay. So when we are use baryon, we use the decay spectroscopy method, and when we are using lithium targets, we are using the
No, the lithium is the same. Lithium is also the only advantage of lithium is that it does not. It essentially, in the case of the fragmentation of lithium, the only hypernuclei you can produce is hypertriton and hydrogen 4, because you cannot produce heavier ones.
Okay.
Thank you. So, any other question? So, yes, if you have, just open your minds, and then. So, if there isn't, let's wait. And but in the meantime, I actually have a couple of questions and one comment. So, you have shown that you use the very in your MAMI spectrometer, you can measure the H4 lambda decay pion with very good resolution. So I'm wondering if you can also measure the helium-4 lambda in this experiment. So you probably know that
helium-4 lambda is not a. I think it's not a two-body decay.
Well, yeah, it's three. Yeah, it's three-body.
So this method relies essentially on the two-body decay, because only then you have a sharp pion momentum.
Right. So you
that is difficult,
only,
unfortunately.
It's not a very it's not a broad distribution. But in principle, can you do that?
Well, it would give a broad distribution, and the yield would be very small. Yeah. So it would be very difficult to get rid of the background under a broad peak.
Yeah.
So this would be the difficult. I mean, this experiment, you see, I mean, unfortunately, like in any case of hypernuclei, there are not too many events, whatever experiment you do. And the more precise you are, the smaller is the yield usually. That's like physics works. And that means you see this yield here is I mean, we have, of course, in some other experiments and more yield, but it's of the order of few 10 events.
Yeah, I saw
if you distribute them over a large momentum range, you won't see that.
Okay, yeah, I got your point. So it's only a very limited statistic. So essentially, if you have more beam time, so you can do that, right?
Well, typically, this is how MAMI runs. The beam time typically at MAMI are 2 weeks, 3 weeks of running time, because we have many different experiments. For this beam time, we had a running time which was quite long, because we also had many things to solve to get this experiment going, because it's a complicated experiment. So we measured, I think, in total something like 60 days or so, which is of course very unusual.
Okay, I see. Another question is that you discussed the neutron star physics and connect to the hypernuclei. So you mentioned that it's very important to measure three-body interaction, but in the rest part, in the second part of your talk, actually, you focus on this very light hypernuclei. So my question is how to connect the three-body interaction to this hypernuclei measurement if you only can do this hypertriton.
Let me. Well, that's why I made a remark that, of course, it will not. One experiment cannot give the answer. We know that. We know, like in heavy ion reaction, when you study the equation of state, you will not get the answer from one single experiment. What is important, of course, that you do this and do studies of all light and heavy hypernuclei in the future. I think hypertriton is important because, let me find the corresponding figure here. It's important because it's once you really can pin down this hypertriton very precisely, like the deuterium, you can really select and pin down certain kinds and exclude certain kinds of interactions. That's why I said it's a question of precision now. And of course, this has to be then embedded in all the other studies of hypernuclei.
Yeah, but this is mainly regarding the hypertridron, is mainly on the two body, right?
No, this is these calculations here. They include also free body interactions.
Oh, okay.
So it's not it's just next to leading order. Next to leading order calculation. So it's already quite advanced. May not be the final answer, but it shows you really how precisely you really have to pin down the binding energy to learn something.
Okay.
And of course, you have to complement that by, I mean, the reason why, for example, we are also doing now very neutron-rich system, at some point you also have to complement that by conventional nuclei, which are more or less neutron, like the tetraneutron, which is very important to understand, but also very heavy hydrogen isotopes.
But you haven't succeeded on the multi-neutron, right?
Yeah.
Okay. Yeah, I have a comment that you have raised that there is a different on the hypertridron binding energy, the difference between ALICE and our star. You know, star actually we do the measurement. So there is a difference that in the star measurement, actually is we have do the two body and three body together. So it's the statistical weight of two body and three body. But in the ALICE result, actually only two body is present in this. This one. So if you look at this ALICE, it is only two bodies. So I think that if ALICE also can add the three body in, then do the two body and three body together, we probably will know if it's indeed real difference or not.
No, that's right. First of all, you see the error, but this is 2 sigma, so deviation, first of all. So as a physicist,
right.
2 sigma means that they are still, to some sense, compatible to a certain level. Second, of course, the argument could be that two bodies and three bodies should give the same result. And if there are differences,
it should be the same. Yeah, I agree.
If there are differences between two and three body decays, it tells you that there may be still some systematics one doesn't really fully understand. No? Yeah. That is right. And I hope that really also Alice will produce new data and you will have probably more statistics. And the main thing of statistics is probably to really see, can one understand systematics much better?
Okay.
Like for the lifetime. I mean, it seems that there was something or still was something wrong in these old measurements. I mean, whether there is also a human component in that, I do not know, because these measurements were so similar at some point, and then suddenly this jumped to these higher values. But it tells you one needs really statistics to pin down and bring down systematic.
In this figure, we also have the new result, right? On the top second actually is our new result.
Yeah, that one here.
Yeah. Okay.
And you see, this is now agrees quite nicely. We now have to see the follow-up experiment of HiFi, which at some point started this. This will be hopefully very soon available, these data from the experiment which we did last spring.
Yeah. Okay. Thank you.
So I think this is something, I mean, which is now converging. And as I said, theoretically, I think we seem to understand what is going on. And it's now really the issue to bring down the uncertainty, experimental uncertainties further to really learn something from the system.
Yeah. Okay, agree. Okay, thank you very much. And let me ask again if there is any other short question. I didn't see. So it is already 1 hour and 15 minutes. So if there isn't any question or comments, I think we should close the seminar. So we thanks again to Professor Josef, and we are looking forward to your visit very soon. Okay.
Yeah.
Thank you.
Yeah. Okay.
Yeah.
Thank you so much.
Yeah. Thank you.
Recording stopped.
Bye-bye.